Hello Fatima, how are you?
I'm fine, sir. How are you?
I'm good. Fatima, did you come by yourself or did the academy inform you?
Yes. What?
Did
I
the
didn't
academy inform
miss
you or did you come by yourself today?
myself. Like,
Okay, alright.
mm, what do you mean myself?
I don't know. In fact, this class has now two Fatmas. So I don't know which Fatma you are. So, don't know. It's alright. Now, so today we are going to. Where were we exactly? We did cross fields, we did. Um, yeah, okay, not bad. Okay. Now, I just want to point out this very, very important equation, and that is when there is a balance of forces within the cross fields. And you know, the cross fields basically means that when electric, the force due to electric field is equal to force due to the magnetic field, and they are also acting in the opposite direction. So because force in the electric field is given by E times Q and force in magnetic field is given by BQV. So you might realize Q is the basically the charge that these forces are acting on the same. So it will just cancel out. So it's going to be E equals to BV. And now you might actually realize this, that this V is equal to the ratio of electric field strength over the magnetic field strength. Okay. I'm just gonna tell you this. This is basically the velocity of charge. This is the electric field strength, and this is the magnetic field strength. Is it clear, everybody? Now, sometimes this formula can be even a bit changed as well. What I mean by this is that because since electric field strength between these two, the plates or the faces which acted like plates are voltage over the distance between them, so we can also write VH over the T like that, and then we can just replace it in the above equation. Then the speed at which it will move would be VH over BD. So I just removed E, replaced it, and then you can get all voltage over BD would basically enable you to find the speed at which these electrons are gonna move. Is it clear, everybody? Any questions? Okay. Now, please do not get scared, okay? Just hold on a second. I want to show you something. Also, if you happen to, if you revised what we did yesterday and you have any questions, please let me know. Till I'm, putting up a diagram. Okay, never mind. Now, so this diagram that you see, it's basically a method of figuring out mass to charge to mass ratio. It's not necessary for you to draw this, okay? I just want to explain it to you because I'm going to send these notes to you anyway, and you can actually just look at them when you have time. So the thing about this is, I just want to remove, wait a second please. Okay, but that's good enough. Okay, alright, now please look at this very carefully. If you look at the first section, basically this section states that it's an electron gun right here. Electron gun basically shoots electrons in the direction that we need towards the cross fields, which are like at the bottom. And this is a sort of a mechanism where the electron beam, this black beam, comes out of the cathode, and anode actually makes it like go in a straight line, and then to make it a beam, and the beam then basically hits crosshair. So if you've played any shooting game, you'd realize that in the sniper scope there is a crosshair basically that sets the target, so just like that, and then the cross fields are there to basically deflect it in either of the directions that you want to. So what you're going to do is now wait a second please. Okay, so now let's look at this then. So first of all, I would like to tell you that this method that we're looking at right now, basically we create a beam of electrons, okay, by heating a metal filament, and that's exactly where this is, as you can see, and then in an evacuated tube. Yes, generally it looks like a glass bulb, okay, like that. By passing current through the filament, and this sort of method is called thermionic emission. Thermionic emission means that you heat the metal so much that the element just shoots electrons, okay. The heated filament liberates electrons, which are then focused into a beam. So as you can see that I've also put it there, the first region is called the electron gun, and it basically helps us select a velocity. So I'll just explain it to you in a bit. It's called the velocity selector, like that. Now, so if we increase the voltage, which is basically, if you look at here, the voltage across the plates, Vp, the electron beam moves to the right, and it moves to the left if we increase the magnetic field strength using the Helmholtz coils. That's basically, the coils are across it, and I showed you Helmholtz coils like here, like this. Okay, now, so I just want to tell you why it will move to the right if we increase the electric field strength, and why it would move to the left if we increase the magnetic field strength, is because what's truly happening is, if you look at this part, this is positive, which means that this plate is positive and the other plate is negative, which truly means that the field is going from right to the left and the magnetic field is into the page. So if you put your index fingers towards the screen and the electron beam is going down, so your middle should be pointed down, so you might realize that your thumb is acting towards the right. Now that is true for a positive particle because these are electrons, so it would mean that the electrons will feel a magnetic force to the left, and because these are electrons, they get attracted to the positive plate, so they will feel electric force to the right. So if you increase the strength of electric field by changing the voltage, the beam will move to the right, and if you increase the magnetic field, it will move to the left. So the moment when both of these fields will apply the same amount of force, that is when the beam is going to hit the screen at crosshairs, which means the beam is traveling exactly straight. Do you guys understand what I'm saying? Yes. Gatika, is it clear? Rafe?
Yes, sir.
Yes, sir.
Okay. Hello Santik, how are you? Okay, now. Keeping that in mind, then you just need to remember that the velocity selection, that what will be the velocity at which the beam is going to enter the field, is done through controlling the electron gun section, like I've wrote. Okay, so we have provided, if you look at it, we have provided a voltage VCA to the plates which accelerates it, and then there's a cathode anode. So let's look at what happens here. So now we are going to look at how the velocity selection is made. So I'm going to put velocity selection, And this is a very simple formula. So what you're going to do is you're providing it with electrical energy by putting a voltage across cathode and anode, and this electrical energy is converted to kinetic energy of electrons as they basically are shot out. Now electrical energy, if you remember, that energy was given by voltage times the charge, okay, or voltage was energy per unit charge, if you remember the formula. So basically this means the charge on the electrons are E, and they are provided with the voltage Ca, which is right here, so that they can be accelerated or moved, and this energy is converted to half times the mass of electron times the v square, and that's what we need. So when you make v the subject of the equation, so it is going to be 2 times E times Vca, that's the voltage provided in electron gun section, divided by mass of electron, root of the whole equation. This basically gives you the selected velocity. And now if you look at the equation itself, you'd realize that basically if you change the voltage, because mass of electron is constant, charge on electron is constant, but if you change the voltage across the electron gun section, it would speed the electrons up or slow them down depending on how much electrical energy you're putting in. Do you guys understand this? The second thing we do is that in the second section we try to control the voltage or magnetic field strength in order to make the beam go straight and hit the crosshair on the screen. So that's what our target is, right? So we're dealing with this. The point of doing all this is that when it would only hit the crosshairs when the force of electric field is equal to force of magnetic field. We've already done this. So the electric field times the charge on electron is equal to magnetic field strength times charge on electron times the velocity that they're entering in, that's the selected velocity. So you might realize that basically the selected velocity defines that what ratio will be of electric field strength over magnetic field, and this way we can easily find out that how much of the how much velocity was there, and you can always look at the charge to mass ratio, which is basically, if you really look at the previous equation closely right here, you can get the velocity from here because you know what the electric field strength is and the magnetic field strength through the Hall probe. You can get the velocity of the particles, you can put it back to here, and from this point you can actually, basically, side note, I'm just writing, you can actually find the charge on electron over mass of an electron by doing just v square over 2 voltage of the electron gun. So this way basically we can find the velocity through the second section, we can put it back to the previous equation, and we can always find the charge to the mass ratio. And this is how we've been doing to find the charge on different particles or different elements that are done, like this, or mass of an electron, something like that. Is it clear, everybody? Any questions? Gatika, does it feel like physics anymore?
Since yesterday it does.
Okay, good. Okay, so Fatma, everything is clear. Ramin and Aman, Suman,
Yes, sir.
and Hasantik, what about you?
Decent.
Okay, that's good. Okay, so there's another method that I would like to discuss now, and I would just a second, please. Let me put in the whole drawing, and then we're going to talk about it. And hopefully today we will be able to look at some questions as well, which are pretty basic in this, not a big deal at all. And none of these drawings really basically are asked to be made, so don't worry about it, okay? So that's all right. You just need to understand that how velocity selection is done, what is the point of doing that, and what is this ratio. That's it. Okay, now this is the other drawing. Now in this one, basically it's a entirely different way of looking at things. So you got the electron, gun sort of thing, and then you have a helium chamber where now you are the magnetic field is into the chamber like that, right? And the beam of electron is going through like this at a certain velocity, of course. So what happens is that in this one, you just need to remember that there is a low pressure helium gas inside the chamber. The electron beam excites the gas, and according to Fleming's left hand rule, it moves in a circular path. We can find its radius of curvature using a traveling microscope. Yeah. Okay, when the meeting ends, so please rejoin. So basically, this helps us find the charge to mass ratio. Let me just tell you how. So first of all, you guys need to understand that when the electron beam enters this way, so it's gonna go in a circle that we've done it like we've done previously as well with this infinite field. The reason it goes like this is because if you check out the force, so the direction of velocity right here is here, direction velocity is here, and then it is like this and it is like this. So Fleming's left hand rule says the index finger towards the crosses in the first part, I'm doing the top one, and then the middle finger to the right. So the thumb shows up for the positive particle because it's negative. The force is here. Magnetic force. In this one, the force will be here. In this one, the force will be here. And this one, the force will be here. So it is causing it to move in a circular motion, right? And because it is moving in a circular motion, you just need to remember that in the previous example, it's the same thing. So the velocity that was selected, okay, that is given by the formula 2 times E times VCA over mass of electron, and we just need charge over mass like that, right? And then what you're going to do is, in this particular part with the helium gases, so we can say within the chamber it looks like that there is magnetic field, and that causes a magnetic force, which is basically providing the centripetal force that's causing it to move in a circle like this, as you can see. So the magnetic force is given by the magnetic field strength times the charge on an electron times the velocity, it's PQE, and the centripetal force is the mass of electrons times the speed at which they've entered, v squared, over the radius of curvature that we know. So from this we can find the velocity, put it back in the previous equation. So that would be velocity and the square will cancel out, so which means velocity is going to be VER divided by ME, and that's how we can find basically the selected velocity, put it back there, and find charge to the mass ratio, as simple as that. Any questions, please let me know. Okay, so generally what they will expect you to do is that you will have to do this one and you will have to do this one on your own, because they expect that when magnetic force is against electric force, so you have to equate them, and when it is moving in a circle you have to equate it to centripetal force. That's all you need to do actually. Now, so first I'll just send these notes to you so that you guys can actually look at it. There, A2 announcement, and crazy. Okay. Oh my god. Okay, and now let's look at some questions and see what we're up against actually. Let's go. Open it up. And now go to $425.
Sir,
Yes.
can you check your WhatsApp?
Okay. I'll do that. What's up? Oh yeah, yes. Of course you can. Of course you can. Alright. So
Alright, sir.
425. Okay. Now let's look at the first example, first question. So in this question, they're saying that there's a current in long straight wire and it's going up, as you can see. So it says on figured pattern magnetic flux horizontal plane ABCD due to current carrying, draw at least 4 flux lines. So what you're going to do is you're going to use right hand Fleming's rule, and that would cause you to draw. The circles should be concentric. Concentric means that ever growing. And like this said, even if they don't say anything, you have to at least make 4 of them. Uh-oh. And make sure that you have the arrows so that they know you know. Like this. Is it clear, everybody? Okay. Now, then it says that the current carrying wires within the Earth magnetic field as a result of pattern drawn is superposed with horizontal component of Earth magnetic field, shows a plan view of plane ABCD. So that's ABCD. So you're looking from the top, with the current in the wire coming out of the plane like this. Okay, wait a second. Write a mark with letter P, a point where the magnetic field due to current carrying wire could be equal and opposite of that of Earth. Okay. So now I just want to tell you this very, very important fact. Let's look at what basically where the Earth magnetic field is. Okay. So we have wire in the middle, that's the wire, okay. And now because the field is going like, it is going out of the page, so you're going to make 4 concentric circles. 1, 2, 3. And the field is like here, 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 okay. So now you realize that basically it says you need to point where the magnetic field due to current carrying could be equal and opposite of that of Earth. Okay. So we need to basically make, wait a second, we need to make a line. It's like this. Now you just need to make arrows, nothing really big here. So let me just show you this. So here the arrows are like, oh my god, wait a second. Here the arrows are like this. Here the arrows are like opposing. So this point, if you look at it, it's basically against the field of Earth. So that's where you're going to write P. Is it clear, everybody? Any questions, please let me know.
So it could be on the second line also, right?
Oh, crap. It could be on what? Anywhere to the left. Anywhere to the left. Okay, so I'm saying Gatika, anywhere to the left is fine. Okay,
So what did you say?
I said anywhere to the left of the wire it is fine. Understood?
Okay.
Okay, then it says this one. It says for a long straight wire carrying current I, a magnetic flux density B at a distance r from the center of the wire is given by expression this. Okay, where P is in found to be this from the center wire and the current is 1.7. So we can actually yes. Okay, so then what you're going to do, it's pretty simple. You just need to find the flux density. Everything is already given in the question, interestingly, right? They say B. Now you have to understand, you got to remember this is 4 pi times 10 raised to minus 7. The current in this was what's the current? 1.7 divided by 2 times pi times the radius is 1.9, so 1.9 got to be converted to meters, and then you can just simply solve this. Like I said, you don't even need to remember this equation, but the value of epsilon is very, very important. So this would be 1.7 divided by 2 divided by pi and divided by 1.9. Oh, there isn't, yeah, okay, 1.9 times 10 raised to minus 2. I made a mistake. So this is going to be 1, 2, 3, 4, 5. So 1.8 times 10 raised to a minus 5 Tesla. Is it clear?
So what do you mean by horizontal component?
The component that's acting like right here, the Earth magnetic field, wherever the distance is from the center. Because you just need to remember, you just need to realize that this is basically, magnetic field is a sort of it is a vector quantity. So everywhere the magnetic field has basically a certain component. Understood? Like that? It's a vector, that's why.
Okay, sir.
Okay, then it says the current in wire B2 is increased. The point P is now found to be 2.8 centimeter. Determine the new current. So basically it's pretty simple. All you need to do is, you just need to remember that in this particular equation, you can put it back in the equation, but that's a very, very, long way to do it. So what I'm going to do is, if I were you, I'd say, okay, I'll see the equation, which is B mu naught I over 2 pi r. And now this is constant, this is constant, these are constants. This is changing and I want current, right? So it means that if I bring r to the other side, so it will be r times b equals to mu naught over 2 pi times I. So basically we're comparing I, so r is proportional to the current. Is it clear? And whenever you have a proportionality, so you can write it like this, r1 over r2 equals to I1 over I2. You can make a ratio like this, and it's as simple as that. Now, previously we had the current. We want to find the new current. Previously the distance was 1.9, right? So what I'm going to do is, and now it is increased to 2.8. So 2.8 over 1.9 is equal to, we want to find I1, and this current was 1.7, I believe. Yep. So the new current is going to be 2.8 over 1.9 times 1.7. That makes it so easy. You can put it back into the same equation, but that would actually take more time. So that's 2.51 amperes. Is it clear? All right, now, okay, this is something we don't want to do. That's almost the same question, so just leave this. And that's what I want to do right now, the only question that's important now. And then we'll just I'll just give you the worksheet for this today, and then you can complete it throughout the weekend. Okay. So now in this one, a negatively charged particle is moving through a vacuum in a parallel beam. Wait a second, please. Okay. They say the particles enter, they have a speed v. The particles enter a region of uniform magnetic flux density of 930 micro Tesla. Initially, the particles traveling in right angles to this. So this is right angle. And then blah, blah, blah. Okay. So now this says that the negatively part follows a curved path. So which means that wherever the center is, the center through that, it says the radius is 7.9 centimeters. The magnetic field, the uniform electric field is then applied to the same region as the magnetic field for the electric field strength of this. The particles are undeviated as they pass through. Now, when the electric field is applied, they just go straight. That's what they mean. So it means a cross field has been applied here. On figure, mark an arrow of direction electric field. Calculate the negatively part. Okay, now check this out, please. If it is moving upwards, it means, first of all, I would like to know that moving upwards would mean that the force of magnetic field must be on the top. And the only way the force of magnetic field, I don't know where the magnetic field is acting. Let me just check out. Force of the magnetic field like this. Okay, this is the direction. This is like this. Okay, yeah. So the magnetic field is basically acting like this. It's going out of the page, and the reason I know this because when you use Fleming's left hand rule, you would actually realize that the index finger should be coming out of the screen. The direction of the current is towards the right, and now the thumb is down, but because these are electrons, so it means the force has to be up. That's why I made the field, upwards like this.
So can you repeat the directions?
Yes, why not? So first of all, what I thought about this was they want us to draw the electric field direction, basically not the magnetic field direction, but I'll still do it. I'm just explaining the magnetic field first because you will have trouble with that. You see, if it is going upward, it means the force of magnetic field is upwards. Do you agree to this?
Yes, sir.
Which basically then means automatically that look at the direction, right? So your thumb should be upwards, okay? Your thumb should be like for a left hand rule, right? Your thumb should be downwards, okay? Or let's just take it upward, doesn't matter. So your thumb is upwards, the index finger is towards the right. Where is your, the middle finger is towards the right. Where is your index finger then? Can you please tell me that?
Out of into the page.
Into the page, right? But that's true for positive particle. So I said whenever there's a negative particle, you just reverse your conclusion. So if your magnetic field was into the page, then right now where will it be? Out. Do you understand? Okay, like that. Okay, now this is not even required. What they want is they want us to know where the electric field is. So electric field means that if it goes undeviated, it means that it is now going downwards, right? That's where the electric force should be. Where does the electrons get attracted to. They do get attracted to the positive side, so this should be the positive side and this should be the negative side, which means the electric field direction should be positive to negative. Do you understand? Like that. That's what you're going to do.
So I didn't get the last part.
Okay, so how could electric force be down on electrons? The electrons get attracted to the positive side, right?
Yes.
So it means that positives would be here. That's why the electrons would feel force right here. And negatives would be on top. So the electric field goes from positive to negative. That's why I've drawn this.
Okay.
Okay, now. So, now it says that calculate the negatively charged the speed v. Okay, now we got to do that. Now, we must understand from the question itself, okay, this should be like 4 or 5 marks or 3 marks. Okay, that's not fair. So much work for 3 marks? That's not fair. So, because whenever a cross fields are applied, which means the electric force must be equal to the magnetic force. The electric force is given by EQ, the magnetic force is given by BQV, we know this. So, we want to find the speed, this cancels out. We can directly apply this too if you want to, like that, okay. Now, the electric field strength is given as 12 kilo, which is 10 raised to the power 3. And the magnetic field is 930 microtesla. 930 micro is 10 raised to minus 6. And now you can simply, find the value. So it's going to be 12 times 10 raised to power 3 divided by 930 times 10 raised to power minus 6. Oh my god, that's too much speed. 1, 2, 3, 4, 5, 6, 7. So it's going to be 1.3 times 10 raised to 7 meters per second. So 1.3 times 10 raised to 7. Do you understand this? Okay. Any questions now? Let me know, please. Okay, now we finish this and then I have to teach my kids. So then it says the charge to the mass ratio. So we have the velocity selection done, right? We have the velocity. And now, because it was moving in a circular motion, we could say that the magnetic force was equal to the force of centripetal, which means it was BQV equals to mv square over r. V and V will cancel out. So BQR will be equal to mv. And we want to find the ratio of what? Mass, charge over mass, which is charge over mass would be equal to V over BR. So that's what we've done. The velocity we've already found, that is 1.3 times 10 raised to 7. The magnetic field strength is 930 times 10 raised to minus 6. And the radius of curvature was given, which was 7.9 centimeters, which is 7.9 times 10 raised to minus 2. So then it's gonna be 930 times 10 raised to power minus 6 times 7.9 times 10 raised to power minus 2, and that's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's 1.8 times 10 raised to 11 coulombs per kg. Is it clear, everybody? Any questions now? So that's how both of the last things that we did are interrelated into this question, and you should always remember this. If you have any questions left, please let me know. Otherwise,